So today we will start our study. Now we will discuss about data clustering. So last 2 weeks we learned about data classification. Now we learn about data clustering. Okay. Okay. So basically clustering works by organizing data points in a data set. So then similar data will be grouped in the same cluster, in a one cluster, but different data points assigned to different cluster. For example, like this. So this because this is similar to each other, like red color, so it is in one cluster, and then the green one will be in one cluster, and this one will be in one cluster. So basically this one, the main point of clustering, similar data group in one cluster, different data should be in different clusters. Yeah. Okay. And here we also will learn about what is intra-cluster distance. Intra-cluster distance means the distance between data points in one cluster, or the similarity between data point in one cluster. Yes. So because we want to group similar data points into one cluster, so this distance, I mean the inter-cluster distance, it should be minimized. However, different data points should be assigned to different cluster. So we have intra-cluster, we have inter-cluster. Inter-cluster is distance between two clusters, like this. So this is cluster, for example, this is cluster 1, cluster 2. Inter-cluster is distance between cluster 1 and cluster 2. And this one, it should be maximized. Why? Because we want different data point assigned to different cluster. So this one we want these two cluster, they have as different as possible. Okay. Okay. So application of clustering. Usually for clustering, the main application, we will use cluster analysis, for example, to understand our data patterns. Okay, so for example, we want to learn about profile of our customers. If, for example, we have 1,000 customers, we work in company, for example, our company have 1,000 customer, for example. If we want to understand each customer behavior, it will be very, very difficult. So with cluster analysis, we can group some similar customer into one cluster. So to analyze it, it will be easier rather than we analyze one by one until 1,000. Yeah, so for example, profiling, customer profiling, we can use cluster analysis. Okay. Another application for cluster analysis, usually we use that to summarize our data. So for example, we have 1,000 customer. That one we have 1,000 customer, and then by cluster analysis we can, for example, divide it into 5 cluster, for example. Then for each cluster we can do a further analysis. Yeah, so it help us to make a further analysis, and it will be easier because each cluster relatively more simple than all clusters. Okay. Okay, if we see like this, a data, this is what usually happen in cluster analysis. We have like this, the original data. How many cluster that we can assign? According to the data visualization, for example, we can cluster them into 2 cluster. But we also can use 6 clustering. We also can use 4 clusters. Yeah, so this issue will also be studied in our discussion, how to deal with this. Okay. Okay. First, we have to know about different types of clustering. First, there is hierarchical and partitioning. Partitioning clustering, if it is a division of data object into a non-overlapping cluster. So we have for partition, we have non-overlapping, means that our data is divided exactly into a number of clusters. So there is no data belongs to more than one cluster. Hierarchical clustering, we call it the result of hierarchical clustering. It will be a set of nested clusters. It is organized as hierarchical tree. Okay, so for example, this is partitional clustering. This is the original point. If we use partitional clustering, then we can slice, for example, slice the data. This is cluster 1, cluster 2, cluster 3. So there is no one data belongs to more than one cluster. Okay. But for hierarchical clustering, in hierarchical clustering, one data, it can be, for example, like this, P2 and P3. Maybe if our point of view is this small one, then maybe P2 and P3 in one cluster, P4 a different cluster, P1 in different cluster, for example. But if we talk about the second cluster, and the area is this, so P2, P3, P4 is a subset of cluster P2, P3, and P4. P2 and P3 is a subset of cluster P2, P3, and 4. Yeah, so this is hierarchical. Okay. So sometimes, hierarchical clustering, usually we will use a dendrogram or tree, hierarchical tree, to represent our data. We can use like this, or it can also be like this. Okay. So they are two different. Another one is exclusive versus overlapping versus fuzzy. So we have exclusive cluster, we have overlapping, we have fuzzy clustering. Exclusive means that one object belongs to one cluster. Overlapping, one object could be belong to more than one cluster. And fuzzy is actually fuzzy, similar like overlapping. So each object can be a member of all clusters. However, because fuzzy have fuzzy membership value, so we will use the fuzzy membership value to represent how certain, how sure that one objects belong to a certain cluster. So, for example, like this. The left one, this is the exclusive. Exclusive. You can see here, like one data points only belong to one cluster. This one overlapping. These 2 points, the overlapping point. So they are belongs to cluster red and cluster green. Okay. In this case, we just can say that, oh, this blue point, these 2 data point belongs to both clusters. If we talk about fuzzy, okay, this is the fuzzy. So each data point has membership value to each cluster. For example, we have cluster 1, we have cluster 2. Let's say this data point, this one, for example. We analyze that one. So we have, for example, this one, data 1. These data points, okay, it's very close to the blue cluster. So maybe the its membership function for blue cluster will be higher than, let's say, the red cluster. So this is the fuzzy membership value. So each of these, if each of these data point will has a value, will have the value, membership value, representing, oh, okay, these data points closer to which cluster. Okay. Okay. There are some types of cluster also. So in clustering, there are different point of view for it. Yeah, that's why we can have many different kind of clusters. Okay, we have well separated cluster, which means that the data points are no overlapping. There's no overlapping point here. All data divided into, for example, like this. For example, we have 3 clusters, and there's no overlapping. So it is well separated cluster. Okay. We also have prototype based cluster. So cluster we have, for example, this is the cluster, the data point inside each cluster. Okay, so each cluster will be represented by what they call it prototype, or the, let's say, the main representation of the cluster. Usually they call it center or centroid of the cluster. It is the prototype of each cluster. So for example, the green one, this is the centroid. This one is the centroid. So centroid is the prototype of this cluster. Okay, centroid, value of centroid, it can be the average of all data point in this cluster. It also can be the medoid, yeah, which means the most representative point of the cluster, yeah, of this cluster. Okay, so centroid, it's depend on the data type. If all data is continuous data, then usually we use average. If the data is categorical, usually we can use it medoid. Okay. There is contiguity base. So contiguous cluster or nearest neighbor or transitive. This is in this type of cluster. This one. A cluster is a set of points such that a point in a cluster is closer to one or more other points in the cluster than any points in one cluster. So let's see. We have each contiguous cluster. Means that when we want to do clustering, for example, then let's see, this cluster, the shape is not common. Usually cluster is like this, and circle. But here, because we consider the nearest neighbor, so for example, let's say I take one data point here, that this data points, they are, the red one is close to each other, so that's why they put it in one cluster. But the blue data point, for example, here, is the distance is far, so they put it into different cluster. Okay. And we also have density base. So instead of only distance, we also consider the density. So let's say, for example, this cluster, the density is very high. It's very dense. The data here is so dense. So that's why the cluster shape is just like this, because they read the density of the data. Okay, and this data will be here. What is it? Okay, so this clustering, we will do clustering, consider not only the distance between data point, but also density. Okay, so here, if we read here, a cluster is a dense region of point. So in dense, for example, it's so close, and this is a little bit far, for example, like this. So usually this data will be grouped together because they are considered the density. Okay, mostly the density-based clustering is used if the cluster shape or the data shape is irregular, or there are some noise or outliers in the data. So that's why we consider the density base. Okay. Maybe I give you example why we consider density base. For example, we have this one. Okay. So if we don't consider density, maybe the cluster will be like this and like this, for example, because there are so many noise. Okay, but if we consider density, then this cluster will be put in one cluster. Okay. Objective function. Some cluster, we have also some clustering algorithms, but here we focus on the objective. So we define the objective first and then the measurement for each cluster to, for example, to decide it, oh, this data belong to which cluster, it's depend on the specific objective. Okay. Okay, so the cluster here will be only focused with the objective functions. Okay, and because we have customized, let's say it customized objective functions, then sometimes the algorithms we have also to consider all possible ways to dividing data points based on this objective function. If our objective is really customized, for example. Okay. Okay. And then, okay. Characteristic of the input data in clustering, it is very important. Why? Because, for example, density, proximity or density, it can influence the clustering result. So density, if we don't consider density and the data is, for example, have some noise, then our cluster maybe will be not very good. Okay, so we have to see the density of the data, whether the data have outliers or not, for example. And of course, the data characteristic that affect proximity or density, usually they are the dimensionality of the data, and then the attribute type, and then some special relationship in the data, for example, autocorrelation, and of course, distribution of the data. So when we do the data clustering, usually we will see first, we will analyze first how big is dimensional for the data, what kind of attribute type, nominal, ordinal, for example, categorical, or ratio data, because the different type will use different similarity measurement, for example. Okay. And distribution of the data, we also have to consider this. Okay, yeah, because from this and with additional, we analyze the outliers, we can decide it, oh, this algorithm for clustering is better than, for example, another algorithm. Okay. Cluster with different size, density, and shape, usually it requires more advanced clustering algorithm. Because basic clustering algorithm, usually they can work well if the density of the data relatively same, and same cluster usually has the similar size. That one, the basic algorithm, it can work well, but of course our data is not ideal, yeah. So we have to see all of these data characteristic to understand the data before we choose which clustering algorithm. Okay, there are at least 3 basic algorithms for clustering. First is k-means algorithms. K-means algorithm, they call it partition-based algorithms. Okay, this one. So do the partition like this. Okay, and then we will have hierarchical clustering, So hierarchical clustering using dendrogram like this. This is hierarchical clustering using tree, and we have DBS scan. DBS scan is special for density-based algorithm. So this is DBS scan. DBS scan will consider the density of each cluster. Okay. In this class, I will try to introduce you three of this. So all of this k-means, hierarchical, and also DBS scan. Okay, we start from the easiest one, k-means algorithm. Okay, so k-means algorithms is one level partition techniques. One level means that if we have the data or data here, we divide the data into several clusters at one time. So in each iteration, we already decided, oh, this is one cluster, one cluster, one cluster, one time. So we do one time in one iteration. Let's say in one iteration, we divided all data. Okay, so one level partitioning technique. Okay, K means it is also a prototype-based clustering algorithms, which means that in K-means clustering, we will use prototype of each cluster to represent all the data. It means that in K-means clustering, we have to find out the centroid of each cluster. Okay. Yeah, so here, this is the prototype base. Means that in K-means algorithm, we should know, we can identify where is the centroid. For example, here. For example, okay. Don't forget, centroid, it can be average or means or medians of the data in that cluster. Okay. K-means clustering, we have to apply this algorithm. First of all, we have to specify number of cluster. So in K-means algorithm, before we do this, we have to know first how many cluster that we want. Of course, many different data points, different number of cluster. So this will be the most this will be the biggest questions before we want to apply the clustering K-means algorithm. How many cluster? Okay. Okay, so this is the algorithm for K-means. K-means, this is a quite old algorithms, but up until now, so many research still use, at least many application for cluster analysis still use K-means algorithm. Yeah, why? Because the algorithms is very, very simple. Like this, you can see, first, we generate initial centroid. Of course, this is random. Okay, and then we assign each data point into the nearest cluster. Okay, and after that, we update the centroid. Then, these two steps, step 2 and step 3, we do this iteratively until until the cluster center is they are not changed anymore. We call it change because if the centroid is still changed or still move to another point to one point to another point, for example, it means that the clustering is not yet settled or not yet convergent. So we have to do step 2 and step 3 iteratively until the centroid is fixed. Okay, to analyze whether the cluster center already converts into one point or not, we have to calculate differences between old and new centroid of each cluster. If the differences is lower than a tolerance limit, then we can stop. In ideal one, the differences is equal to 0, means that it is not moved anymore. Okay, but sometimes it is very difficult to find this condition, so we set a tolerance limit. Okay, let's see. Yeah, for example, like this. This is the result of clustering. So here you can see this is the visualization of cluster algorithm for each iteration. Okay, for example, this is the original data. Yeah, and then we are going to do clustering, and we divide it into 3 cluster. Okay, I will divide it into 3 cluster. So first step, we generate initial random centroid. So this plus means that we have 3 initial centroid. Because this is random, then the data assignment still not good. You can see this, for example, the green one is into one cluster, blue one into one cluster, and the red one into one cluster. So after we set, or after we generate initial centroid, we assign each data into the nearest center. Okay, then after that we update the centroid. Okay, update the centroid, so the centroid will move. This is in the second iteration, the centroid move. Of course, the centroid of each cluster, it will move to where is the most data point located. Okay, then we it update it, and then we assign again each data point into the nearest cluster, and then we update again. So this in iteration 3 it move again the centroid. Okay, assign again to the nearest one, and always move like this. So the data centroid, the cluster centroid is always move until when we stop, until it doesn't move anymore. So we can see that in iteration 5 and iteration 6, the centroid of each cluster, it doesn't move anymore. Let's see, this is the cluster 1, for example. This is cluster 2, this is cluster 3. So they don't move anymore. So we can stop. They don't move, or they don't change the location, or even they change the location, maybe it is not significant because it's very close. Yeah, so we can stop this, and this is the final result: cluster 1, cluster 2, and cluster 3. Okay, let's use real data to make it more clear. Okay, for example, we have 6 data point: 1, 2, 3, 4, 5, 6. Okay, first step, generate initial centroid. Of course, it is random. So I want to divide it into 2 cluster. We have number of cluster 2. So we have to generate 2 centroids. So for example, this is centroid 1 for cluster 1. This is centroid 2 for cluster 2. I get this number randomly. Okay, and if you ask me what is the range of centroid, usually I see the range of the data point, highest or the biggest one. Of course, I don't want to set a centroid far away from the data, so I choose a generate random in range of the data point. Okay, or to make it clear or fair between attributes, if one attribute is for one attribute is age, one attribute is income, for example, the value is very far different to each other. So for clustering, it is very recommended to use data normalization before we do clustering. So the data, it's we know the range of the data. The data has been normalized, so it's easier for us. Okay. Okay, continue to k-means. So here because we want to divide it into two clusters, so I have two centroid here. M1 centroid 1, M2 centroid 2. In the picture, this one is 7, 4 here. This is clustering 1, centroid 1. This one centroid 2. Okay. Then after I have these two centroid, in the next step is I assign each data point into the nearest center. So to get which one is the nearest one, of course, I have to calculate distance each data point in to each cluster. For example, this is the first data point, 0.9 and 0.8. 0.9, 0.8. So I use, let's say this one, I use Euclidean distance. Euclidean distance. So I calculate Euclidean distance between data point 1 and centroid 1, for example. So I use it like this. 0.9 minus this one to center 1, 0.7 square plus this one 0.8 minus 0.4 square. The result is this one, 0.45. So this is the distance from data point 1 to centroid 1. And we also calculate distance from data 1 to centroid 2. Okay, using Euclidean distance. So here, 0.9 minus this one, 0.4 square plus this one, 0.8 minus this one, 0.1 square equal to this, 0.89. So we have like this. Data 1, distance to centroid 1 is 0.45. Distance to centroid 2, 0.81. 86. So we choose which one is the closest one or which one is the lowest one. So here is lower than to centroid 2. So for data 1, we assign this into centroid 1. Into cluster 1, because cluster 1 is closer than cluster 2. Okay, so data 1, which one is data 1? This one is M1, this is M2, 0.9, 0.8. Oh, this one is data 1. So this belongs to cluster 1. Okay, and data 2. For data 2, we also do the same thing. We calculate distance between data 2 and centroid 1 using, for example, Euclidean distance. So this will be 0.8 minus 0.7 square plus 0.8 minus 0.4 square. Result will be 0.41. And we also calculate distance from data point 2 with centroid 2. Using the using the equation Euclidean distance, so we will get the distance is 0.81. Okay, so we choose the smallest one. So data point 2 will be assigned to cluster 1. Okay, this one, D2 also cluster 1. We do this for the rest of the data. And finally, we get like this: data 1, data 2, data 3 is this one, 0.1 and 0.2. This data 3, and then we have data 4, data 5, and data 6. Okay, so in one iteration, after one iteration, we will have this in one cluster, this in one cluster. Okay, and then after we assign the data, we have to recalculate the centroid. So how to calculate the centroid? We have to calculate average of the data point in one cluster. Okay, so this is for cluster 1. So for cluster 1, we take all data belongs to cluster 1. So it is data 1, data 2, and data 6. So this one, data 1, data 2, and data 6. Okay, so this is the first dimension, and this is the second dimension. We just use, this is the average. So average 0.78 is the average of 0.8, 0.8, and 0.79. 0.85 is the average of this. Okay, so this is the new centroid for the first cluster. Okay, so the cluster centroid 1, the new one is 0.85, 0.78. Okay, and then we also calculate for cluster 2. Cluster 2. Okay, so which data point belongs to cluster 2? Data 3, 4, and 5. 3, 4, 5. Again, we average data, all data in this cluster. So here, the average of 0.1, 0.3, 0.2 is 0.2, and average of 0.2, 0.1, 0.2 is 0.17. So the new centroid for cluster 2 is 0.2, 0.17. Okay. We have the new centroid. Then, before we decided whether we want to stop or not, we have to calculate distance between new cluster and old cluster. Here, of course, if we in K-means, if we talk about cluster, then always refer to centroid. Okay, so this is the old centroid, and this is the old centroid. This is the new one, new centroid. Okay. Here we calculate distance. For example, centroid 1 and the old centroid 1 and old centroid new. Distance is this. This is for the second cluster. Distance is this. And let's say the easy one is I use average of these two clusters. Okay. So for average, for example, 0.3. If this distance is still higher than the tolerance limit, then we have to continue back to the step 2. But if this value less than the tolerance limits, it means that we can assume that, oh, this new cluster is not really different with the old cluster, so we can stop. Okay. If we decided not to stop, then we back to step 2, like this. We back to like this again. But this centroid, it has been updated. So the centroid is updated into the new centroid for the next iteration. New centroid. So for the new centroid, M1, M2, they are different. X, Y. See, the new centroid is 0.85, 0.78, 0.2, 0.17. Okay, so if we decided not to stop, then we back to step 2, but the centroid is updated using the new centroid. Then we calculate again the distance for each data point to each cluster, and we assign them again to the closest centroid, and we recalculate again the centroid. So we do this step 2 and step 3 and also step 4 until stopping criteria is met. Okay, any questions?
Clear for me.
Okay, so we continue. It's quite simple, yeah. The clustering algorithm for using k-means is simple. Computational time also for computational is also very usually it's very fast. Okay, so that's why the k-means clustering it is actually very simple iterative algorithm. That's why we still use this until now. Okay, and the most basic one, initial centroids, choose randomly. Okay, but because we choose initial centroid randomly, sometimes the result it can be different. For example, we do the first run, and the result, for example, this is the data point. For example, for the first run, for example, after several iteration and then it's converged, but the result is like this: first cluster, second cluster, the third cluster. But next time we run again with different initial centroid, maybe the result will be different. For example, it will be like this, second cluster and the third cluster. Yeah, so it's really common happen if we use k-means. Okay, this one centroid is typically the mean of the points, but it can be also defined, for example, using medians or the others definitions. Most of the convergence happens in the first few iteration. Yes, so sometimes we don't need many iteration, because in only few iteration it's already converged in one result. Okay, and this is the complexity of the clustering. Yeah, so it's not really high actually for the complexity. And how to evaluate our result? So for k-means, here we use actually there are many cluster validity, later I will show you, but the most common measurement and the most basic one, we use the sum of square error. So the sum of square error basically is the total distance between each data point to the cluster centroid. So for example, we have data 1, data 2, data 3, data 4, data 5, for example, and we have centroid 1, centroid 2. According to the clustering, 1 to 3 belongs to one cluster, 4, 5 belongs to one cluster. Okay, so SSE, sum of square error, is like this: distance between data 1 to centroid 1, data 1 to centroid 1. And then data 2, distance between data 2 to centroid 2. Okay, and distance between data 3 to centroid, centroid 1, still centroid 1. Why still centroid 1? Because data 1 to 3 belongs to first cluster. But for data 4 and 5, because it belongs to cluster 2, so distance between data 4 to centroid 2 and data 5 to centroid 2. So SSE is the total of this, total distance. This one is the SSE. Okay, total distance through them. And we prefer SSE is the lower one. So less the smaller SSE, the result is better. Why? Because if we back to the main objective of clustering, we want the data in one cluster is as similar as possible. It means that similar as possible means that smaller distance. If the, for example, data 1 and data 2, the most similar is if the data is very close to each other. It means that the distance is very close to each other. So the SSE will be low if the data is very close to each other. Okay. Yeah, so SSE is the total distance between that each data to its cluster centroid. Okay, advantage and disadvantage of k-means. Okay, as you know, advantages, it's very simple algorithm, and because it is very simple, then it can work very fast. Okay. However, of course, because the algorithm is very simple, so they have also some problems. Means that the result is not perfect. Then there are some drawbacks of the k-means. Okay, so let's see one by one. The first one is the problem with the initial centroid. Okay, first one is problem with the initial centroid. Okay, why the initial centroid can give us problems? Okay, let's see this picture. Okay. From the left picture, we have three cluster. For example, this is the first cluster, second cluster, and the third cluster. Okay, this is the ideal result. For example, this is the optimal one. Let's say this is the optimal one. Okay, once time, for example, if we do k-means and then we generate randomly initial centroid, and maybe the first initial centroid is here, here, and here, for example. And then over the time, over the iteration, the first centroid will move to this point, for example. The second centroid will move to this point. The third centroid will be moved to this point. So the result will be like in this the left picture, perfectly divided into three clusters. But for example, sometimes we run again, but this time we are not lucky enough. So the initial centroid, for example, one here, and one here, for example. Okay, and over the time, over the iteration, first cluster, first centroid will move to here, second centroid move to here, this one, and the first centroid will move here. So in this case, maybe the first cluster I think is okay, still okay, for example. But the second cluster, let's see, like this. Okay, so see, it's like overlapping. It's not clear enough for the this one, the differences between cluster 2 and cluster 0. Yeah, of course, SSE here is less than the SSE, the second one. And because we can see that, for example, distance from this data point to this cluster is quite far. And compare with if we use this as the centroid, then the farthest data may be here. Yeah, so this condition is it's very commonly happen in k-means. So if we the initial centroid is not very far away from the real cluster, for example, this situation may happen. Okay.
Dr. Farah,
Yeah.
excuse me.
Yeah.
Uh, for the previous slide, uh, on the left side, you're the one who clustered it, right?
Mhm.
And then if you did the iteration, which would be on the right side already after the iteration, right?
No. This is
Oh,
this is the first time. This is the first running. For example, the same iteration. Iterate 10 iteration. This one also we start again. We do another k-means, but the result can be different.
oh, okay. But every iteration, it's as you said earlier, it may happen that, for example, the second iteration that you would be doing, it would be a different cluster already.
Yeah.
Will you be the one still to cluster it, but it would look different because of the centroid? Correct.
Yes.
Oh, okay.
Because the centroid is different. The initial centroid is different. Okay.
Oh,
This is
thank you, thank you.
okay. Hopefully this is more clear. For example, we do 2 times k-means with the same data. For example, the left one, the left one, iteration one. Oh, I changed the color. For example, centroid one, centroid two, centroid three. Okay. Next iteration, move to here. Okay. Next iteration, move to here. And of course, the data also move, yeah, changing. Cluster, sorry, iteration 4 moved like this, iteration 5 like this, iteration, and iteration 6 is like this. So this is the final result. First cluster, the green one, second cluster, the red one, and third cluster, the blue one. Okay, looks good. Yeah, because it's a visually it is a well separated cluster. Okay, but then we do another running of k-means. Okay, so for the another running of k-means, for example, we get this is the first random initialization for centroid 1, and then this is for centroid 2, and then this is for centroid 3. Then for the next iteration, iteration 2, move to here. This is for the second one, and this is for the third one. Okay, iteration 3, not changed very much, so still around here. Iteration 4 also still around here. Iteration 5 is also still around here. The algorithms, they only calculate differences between new cluster and old cluster. So you can see that in iteration 3 to 4, 4 to 5, the centroid location, they don't change. And so they stop. Okay, but the result, you can see this, the green one first cluster is like this, and then the blue one second cluster, and the red one is the third cluster. Okay, yeah, so you can compare final result. This is for the first one, and this is for the second one. See that in the second one, with different initial centroid, we can get totally different result. Yeah, a totally different result. So that's why k-means, because it starts from random initialization, so the result can be different, very different. We do it one time, and then another time we do it again, the result, it can be very different. So it is quite sensitive with the result, is quite sensitive with the centroid, initial centroid. Okay, yeah. So is it clear, Arfin? This is the
Yes,
question.
doctor. Yes,
Yeah,
Dr. Fry. Thank you.
you're welcome. Okay. Uh, okay. So what happened? What happened? Sorry. How to deal with this problem? Because we don't want to. Sometimes we can get the bad one. Sometimes we get the good one. Yeah. So how to deal with these problems? First, we do k-means several times to see how is the result. So maybe we do the same data. For the same data, for example, this is if we do 2 times k-means, totally different. So we run again for the third time, for the fourth time, fifth time, until, for example, let's say 30 times for the same data, and see which one is the most commonly happen. We hope that this should be the first case should be happen more than the second case, so we can choose, oh, this is the first one is the best cluster. Okay, so we choose most frequent case happen. Okay, so we do running the k-means several times. Okay, the next one, we can use some strategy to select the initial centroids. Okay, so there are so many strategies to select a better initial centroid. So this one we use the strategy. The objective is to get a better initial centroid. For example, we can use hierarchical clustering to determine the initial centroid, because hierarchical clustering, it doesn't need, it doesn't require the initial centroid. Okay, maybe later after we learn about hierarchical clustering, we can come back to here and I will show you how to combine hierarchical clustering with k-means. Okay, another one, we can select more than k initial centroids and then select among these initial centroids, select the most widely separated. For example, if we back to this picture, okay, no. For example, this is the first case. 1, 2, 3, 4, 5, 6. But we want to actually we want to do on to 3 cluster, for example. But we choose more than 3 initial centroids. And then we calculate distance to each other. For example, to here, to here, to each other, to all of this. Okay, and then we choose the most widely separated. Why we choose the most widely separated? Because we hope that the clustering result, the centroid will cover all data points like this. Will cover all data points, will cover all location for the data, will cover all possible solution of the data points. In compare with if we have, for example, the same data, then a centroid very close to each other. So in this case, usually the clustering result will not be very efficient because the initial centroid is very close to each other. So it's like only for one cluster. Okay. And based on my experience, another option, yeah, for to choose the initial centroid, we also can, for example, we choose some data points randomly as the initial centroid. For example, the green one is the data. Then let's say I choose 3 data points randomly. For example, this one, and then this one, and then this one. For example, as the initial centroid. Yeah. So we have many strategy to do this. Or you also can consider to, for example, let's say we have, for each attribute, we know the average and we know the range of each attribute. Let's say this is the average, this is the minimum, this is the maximum. So we choose one here, value, one near the minimum, one near the maximum, for example. Yeah, as the initial centroid. Okay. Okay. The second problem with the k-means. K-means, we have to determine how many number of cluster. Okay. For the benchmark data set, for example, or if the data we know already, oh, this divide it into 3 clusters, for example. This will not be a problem. But for most of the case, especially for the real case, sometimes we don't know how many number of cluster. If we back to the very early slides, I back to here. Like this. Okay, let's say, oh, I have this data. We do data visualization first. Okay, so the first thing, we can use data visualization to see, how the data patterns, how separating the data based on the data visualization. Okay, for example, this is the data visualization result. If we see the data, we can guess how many suitable cluster for this data. But then maybe different people will have different opinion. For example, oh, I prefer 2 cluster. This is 1 cluster. This is the second cluster. Okay, 2 big clusters. But maybe maybe you have another opinion. Oh, I think the first cluster is too big, so we can divide it into 4 cluster. This is 1 cluster, 1 cluster, 1 cluster, and 1 cluster, which is also okay. If we see from the picture, 4 cluster is okay. Maybe another person say, oh, no, I want to divide it into, I think it is 6 clusters. So someone will think that like this, which is also correct. So 2 cluster is acceptable, 4 cluster is okay, 6 cluster is also okay. So which one? Yeah, even though we use data visualization, but sometimes it can be different opinion, ambiguous. Yeah, so how to decide it number of clusters for k-means? Okay, first we back to see the cluster evaluation or the main objective of clustering. The main objective of clustering is lower SSE, as lowest as possible, the SSE. Okay, so we can do elbow method. Elbow method, actually, we will do several times k-means using different number of cluster. Okay, basically, a higher number of cluster, SSE will be lower. Yeah, so if the k number of cluster is increased, then the SSE will decrease, of course. But if we have too many number of cluster, it's like the cluster is too small, so it is not significant. The clustering result is not significant. What I mean not significant is, for example, we have 6 data point, 1, 2, 3, 4, 5, 6, for example, and then we divide it into 3 cluster. Okay, so we can still analyze this, group this. But if the k number of cluster is increased, for example, we divide it into 4 cluster or 5 clusters. So maybe this is 1, 2, 3, 4, 5, for example. So you can see that this cluster is standalone. Another one, so it's like we don't do clustering because the number of cluster is too high. There are so many clusters, so the data is not simplified. We don't simplify the data because number of cluster is too high. Yeah, so there's a trade-off between number of cluster and SSE. So what we want is, we want to have a small SSE, but the number of cluster is not too high. So what we do is we use elbow methods. Okay, elbow method is like this. Elbow methods, it use a trend. So we make a graph between in the x-axis is number of cluster, and in the y-axis is the SSE. Okay, okay. So here in clustering, if we add number of cluster, SSE will decrease. Okay, for example, like this. This is the only one cluster, for example. And then if we set two cluster, the SSE will decrease significantly, drop like this. And then we add another number of one more number of cluster, still decrease. We change to 4. 4 is here. It's decrease. But more number of cluster, the differences is not significant. You can see that the line is still becomes more horizontal. It means that the differences of SSE when we add more cluster is not significant. So at that point, we set that, oh, okay, so the elbow point, this is the elbow point, is the appropriate number of cluster. Okay, so the elbow methods, how to use the elbow methods, we make a graph between number of clusters and SSE like this. Okay, so we do clustering, k-means clustering several times, and then we choose which one is the elbow point, and that is the correct number of cluster. Okay, so in this picture, the elbow point is 3, or some maybe around 3 or 4, 3 or 4, 3 or 4 number of cluster. Okay, so this is one example. Okay, any questions for elbow methods?
It's the same like factor analysis, right? For this one, the
Oh
concept.
yeah, yes.
Okay, I got it.
Okay, okay. How about the others? Is it clear? Okay, no question. I will continue. Okay, another problems. How if our cluster is empty? Okay, why cluster is empty? So we have, for example, uh, data point, data point, data point, for example, and then I have what is this? Centroid, the first centroid, second centroid, the third centroid, for example. Okay, and then we assign the data into the nearest centroid. So maybe this will becomes one cluster, and this will be one cluster. Okay, the third centroid M3, for example, because this centroid is very far away from other data, so no data assigned to this centroid. Okay, in this case, our clustering result, which should be 3 cluster, it becomes only 2 cluster because the third cluster is empty. Okay, so this result is also not good. Okay, so how to handle the empty cluster? Okay, so first there are several strategies. For example, we can choose point that is the farthest away from any current centroid. Okay, and then we choose a replacement centroid for the cluster that has the highest SSE. We also can choose this. Okay, for example, the first one, use the first one, for example. We have we have the distance of each data point into each cluster. For example, this one to here and this one to here. Okay, we calculate that, and then we choose the farthest point. Means that the point which has the highest distance. For example, let's say this is the highest distance because it is the far away from the center. And so these data points will be used as the third centroid instead of this. So here the third centroid is moved to here. Okay, this is the first one, first strategy. Okay, and then the second strategy, we can also divide it a cluster which has the highest SSE. So for example, solution number 2, for example, this is the first cluster, and then this is the second cluster. This is the second cluster, for example. Of course, SSE1 is less than SSE2. Yeah, because SSE2 is very big. So the big cluster will have a relatively higher SSE. Okay, so we find out which one is the cluster which has the highest SSE, and then we are going to divide it into 2 clusters to make it smaller, the SSE. So we divide two cluster. We divide the biggest cluster into 2 clusters. Okay, this is the second one. Or if we, the third one, okay, if there are several empty cluster, okay, then the above can be repeated several times. There are some empty cluster. If we set like higher number of cluster, this case it may happen. Yeah, so maybe there are more than one cluster which is the empty cluster. So we can do this several times until all cluster is now empty again. Okay. An alternative approach is to update the centroid after each assignment. Okay, so we can update centroids after each assignment, but for this alternative, I really seldom use this because it takes time. You can imagine like we have M1, for solution 4, for example. After one data assignment, then we calculate the centroid, adjust the centroid again. Another data assigned, and then adjust again. So it takes so much time. Okay. Okay. So this is what happened with the empty cluster. Be careful with empty cluster. Okay. But from empty cluster, we also can get, it can also indicate maybe it is a noise or there's some noise in the clustering. Okay. So maybe we can identify noise also with this way. So for example, the data is like this. Data, and maybe this is one, this is one, this is one, for example. Okay, and after several iteration, for example, this belong to one cluster, this belong to one cluster, for example, and this belong to one cluster. Let's say I have 4 clustering, and another one is only one or only one, like this. And these 2 points always be alone, for example. So there is one or more cluster which only have one data point, or the number of data in one cluster is always very, very small. So in this case, we can go check again and whether the data is outlier or not. So if this data is outlier, maybe we can delete this because it will influence other cluster. Yeah. Okay, so if there is one data point which is always be different than each other, and the number of cluster is always small, or only that data, so maybe it can be also a noise. Okay. Limitation of k-means. Okay, so k-means has problem when clusters are in different size, different density, and non-globular shape. Later I will show you what is this. And also k-means will has a problem when the data contains outliers. So actually k-means algorithm is very sensitive not only to the initial centroid but also outliers. Okay, so let's see from the first one, different size. Okay. Like this, for example, the size of the cluster is different. This is the first cluster, small cluster. This is the second cluster, is a big cluster. This is the third cluster, a relatively small cluster. So in k-means, maybe the result is like this. 1, 2, 3. Nah, okay. Because k-means, it's usually have like it's prefer like the same number of data. Yeah, because in some area. Okay. And different density, it also can give us not quite good result. For example, this is the original data point. For the red data point, we can see that the density is low, so it's relatively far away to each other, and although they are in one cluster. And the blue one density is quite high, and the green one is also quite high. So if we consider also the density of the cluster, then the result should be like this: cluster 1, the red one; cluster 2, blue one; and cluster 3, the green one. Unfortunately, k-means it don't consider density. So the result may be like this. So this one cluster, blue one cluster, and the red one cluster. Okay, yeah. So class centroid k-means it don't care about the density. Okay. Another problem if the data shape is non-globular. What is non-globular, and why it becomes a problem? Because, for example, k-means always represent the data always represent the cluster as the centroid. Let's say this is the centroid. So the data around the centroid will be assigned in the same cluster. And because the radius here relatively the same, and so it most of the case centroid, the shape of the center is always like round, like this. 1, 2, 3 cluster, for example. 2, 3, 4, 5, for example. Yeah, it is globular shape. But what happens if our data is like this? For example, the red one is one cluster, like this, and then the blue one is another cluster. It is not in the round shape. K-means, the result of K-means may be like this. So this is the one cluster, and this one will be the second cluster, because they prefer like in radius circle like this. Of course, the result also not good. Okay, so how to overcoming the k-means limitations? For example, one solution is to find a large number of clusters so that each of them represent a part like this, part of natural cluster. Okay, so at the first time we set a large number of clusters, but then in post pre-processing we will put small cluster together until we get the number of cluster that we want. For example, we want to have 3 cluster. We have 3 cluster, and then for the first k-means, instead of set k equal to 3, we set, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We set k equal to 10. Okay, so in this case, we will have 10 centroid. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, for example. And of course, each cluster representing by each centroid. Okay, now after we have 10 small cluster, we can imagine that, oh, now we have 10 data point. So we have 10 cluster, small cluster, sorry. We can imagine, imagine that we have 10 data point. So then this data point we do cluster into only 3 clusters. So the result may be like this: 1, 2, 3. Okay. The same way also can be applied if like this. Yeah, this one, if the density is different, for example. Yeah. So we also, instead of directly using 3 data point, we use directly a cluster to 3. We do we divided data into 10 clusters. And then we treat them as 10 data point. So we can get a better cluster. The same way also for density, problems due to density. Yeah, so basically we'll choose a higher number of cluster and do post pre-processing. Oops, sorry. Post pre-processing. Okay, so this is the pre-processing and post-processing that should be done in data in k-means. Yeah, because there are some disadvantage or some drawbacks of k-means. So we have to do pre-processing and post-processing for k-means. Okay. For example, this is the minimum effort for pre-processing. At least we have to do data normalization and we have to eliminate the outliers before we do k-means. And for post-processing, for example, this one, we can eliminate some small clusters that may represent outliers. So for example, this is the clustering result. One cluster, one cluster, one cluster, but we have one cluster. And this situation always happens. We always have 2 small cluster. This is small cluster, this is small cluster. So in this case, maybe we can consider this 2 point as the outlier. So we can delete this because it's always far away from other and only small number of data. And so we can eliminate it because it may represent the outliers. Okay, Next one is split loose cluster. For example, cluster will highly class. Sorry, I copy this 2 times with high SSE. Split loose cluster. Split loose cluster is, for example, we have usually this is the large cluster. For example, one cluster, and we have like this actually in one cluster. Okay, so cluster 1 is okay, cluster 2 is okay, but cluster 3, this one, for cluster 3, the SSE may be very high. Distance between a data point, the farthest data point into the centroid is very far away, for example. So in this case, we can split this cluster into 2. Okay, so the result will be maybe like this: cluster 1, cluster 2, cluster 3, and cluster 4. Okay, and if we can split the cluster, we also can merge cluster that are very close to each other and relatively have low SSE. So if there is a cluster very close to each other, always maybe one here, one here, and one here. So because after several iterations, then these two clusters always be very close to each other. So maybe we can combine into one cluster. And of course, the low SSE because the number of cluster is very small. Yeah, so we can combine them. Okay, any questions?
Artvin Ong, can we later try your data if you are okay? Artvin
Oh,
Ong.
okay.
Is
Okay.
that
Sige.
okay? Is that okay, Dr. Farah? So I think everyone has the data in the similar
Yeah,
questionnaire data. So why don't we
yeah,
just why don't we just start give one example how to do the how to do the clustering, and then after that we can because I think everybody can do that by themselves after this one.
yeah. You have to do that.
Okay. Okay, Artvin
So
Ong later after all of this, yeah.
mm, I think, or maybe now I can show you using Iris. It's very simple. So wait, I will open my Python first. Then I
Artvin
will
Ong. Okay.
anaconda. Okay. So you also can try if your computer is ready, you also can try to do the same thing. Oh, let me open my file. Mm, mm, mm. Okay. Oh, I changed my share screen first. Okay. So okay. So I'm showed my Anaconda navigators. Can you see this?
Yes, Dr. Fed.
Okay, wait, slow. Sorry, wait. For practice, I will use Iris dataset. Okay. Oh, so slow. Okay, then what happened with my laptop today? It's so slow. Hmm. Okay. Okay. So okay. First, in sklearn, they have they provide k-means package, so we can use this package. Okay, and later I will tell you what is this matrix. So matrix is the similar like SSE. So for now, I will skip this. And again, this one, this is for the after I input the data. Oops, after I input the data, then don't forget to do data normalization. Okay, so this one, data normalization. For this data, I use min max scalar. Preprocessing min max scalar. So for preprocessing, I use preprocessing package. This one, sklearn preprocessing. Okay, and then k-means. This one is the k-means for uh, iris have 3 clusters. Okay, so iris have 3 clusters. So okay, let's just play. Okay, so this one is this one is the result of iris dataset. So it's become one cluster, second cluster, and the third cluster. Yeah. So basically, it's quite simple because the package has been provided by Python. So we can use like this k-means. Yeah, you can number of n cluster is the number of cluster. Okay, and actually there are many parameter setting here. If we go to this one, sklearn, sorry, sklearn and k-means. This we can customize our k-means. Okay, first, this is the initial parameter. Sorry, the parameter for the package. First is number of cluster. We can set a number of cluster equal to how many. Okay, and then init init this one. It means that we want the algorithms to do the initialization. We know that the basic one, this is the initial centroid. Okay, if we don't choose, if we don't set these parameters, then our k-means program will choose random initial centroid. So the default is the random initial centroid. In my case, this one, I don't choose the initial centroid. I don't set the initial centroid. So they will use random initial centroid, just like what I just show you here. Yeah, this is the initial centroid randomly. Okay, but here they have provided us with some strategy for the initial centroid. For example, they have k-means plus plus. K-mean plus plus means that it selects initial centroid center for K-means clustering in a smart way to speed up convergency. Okay, so this Python have different way to find the initial centroids. Okay, and what else? Oh, only two. They only provide only two, random or K-mean plus plus. Okay, and they also will give us n init or n initials. The default is 10. What is this? This one is number of time the k-means algorithm will be run with different centroid seed. The final result will be the best output of the initial consecutive runs in the inertia weights in terms of inertia. Okay, so this package, because they know that k-means is so initial centroid is the biggest problem of k-means. Okay, so this package they have they provide us with some way to deal with the random initial centroid. So uh, the first one is this strategy, and the second one is like this. So basically, the algorithm before they give us the result, they inside the package, it has tried at least 10 times. So they try at least 10 different initial centroid. Okay, and from this 10 result, they will give us only the best one. So although we, for example, like this, I run one time and I get this result, but actually the program is already run 10 times, 10 with 10 different initial random centroid, and they only give us the best one. Okay, if you want to increase, then it is also possible. You just change this one. Okay, max iteration. This is the number of iteration for k-means algorithm for a single run. And this one, TOL, is the tolerations. This one, basically max iter and toleration, these two, they are the stopping criteria for k-means. If we use maximum iteration, then the maximum iteration is the stopping criteria. If we use tolerancy, then we use differences between old and new centroids as the stopping criteria. Okay, and this one is pre-compute distance. Let's see, pre-compute distance faster but takes more memory. Okay, auto, it means do not pre-compute distance if n samples. Okay, honestly I never use this. Okay, verbosity mode, I also seldom, almost never use this. Random states, random state is control the random seed. Yeah, and this one, usually I skip this. This one also skip this. Okay, and this one, algorithm full, auto, Elkan. Okay, k-means algorithm to use. The classic EM style algorithm is full. The Elkan version is more efficient on data with well-defined cluster by using triangle inequality. Okay. Okay. And this one, the output that can be provided by this package. Okay, so if you want to observe this package, maybe you can try with different parameter setting like this. For example, this one, the initial, we don't use random, but we use k-means plus plus, for example. Yeah, so iris is quite easy. So the result is this is already the result, the optimum result. But maybe for other complex data, you can try with different initial centroid strategy like this. Okay, any questions? No questions?
Dr. Farah, for the iteration, would you recommend to only use the first one, K means plus plus, or default 10 or 300? I mean, what would be best?
You mean this one or this one?
Yeah.
Okay. Um, so first init and end init, these two, it will these two will be about the initial centroid, but maximum iter and toll is about the stopping criteria. So wait, let me add. Okay, uh, init and init and init. This two is about initialization, and max iter and toll. This is about stopping criteria. Okay, so we can compare these two because this is about the initialization, and we can compare these two, between these two, maximum iteration and tolerance. Okay, if you ask me which one is the good initialization, the question we have two options: K means plus plus or random. Okay, K means plus plus is better than random, of course, but then if we choose the better one, maybe the computational time usually it will be longer than the random. Okay, and in it is a number of centroid seed that we try. A higher number, if the n is higher, the probability to get a better result is also higher. You can get the better result, but the computational time, the time is also increased. Yeah, so we can get a better result, but as a consequence, the time usually will be longer. Okay, and for the max iteration, you can try for stopping criteria higher number of iteration, the result maybe usually it will be a better result, but again the computational time also will be increase. It will increase. Okay, also the tolerancy. If the tolerancy is decrease, so the if the tolerancy uh what nearby zero, then the computation the result will be better, but the time is also increased. So if sorry, so how to, in practical, how to determine this parameter? First, we have to see the data. We use data as visualizations to see how difficult our data is. For example, our data is like, let's see, we should have overlapping. Okay, let's see. Okay, for example, data is like in the left picture. They already well separated. By using our eyes, we can see that, oh, it's easy because it's this one is close to each other, this one is close to each other, and they are different, far away. Okay, so it is quite easy, relatively easy. So the easy data for clustering is if the data is already the cluster is very, like, it's quite obvious. This one cluster, one cluster, one cluster, for example. it's obvious. Okay. Which one is the difficult one? For example, uh, there are so many overlapping data. For example, like this. So is it like this, or like this, like this? We don't know. We use data visualization, and we see that too many data, overlapping data, like this. So this is will be more difficult rather than this one. So in that case, if your data is like the second one, the difficult one, then my suggestion is, for example, for the initialization, then we use k-means plus plus, or n inits, we use higher number, for example 20, for example. Okay. And also the stopping criteria, for example max items, maybe I try, okay, usually I try from the relatively small, let's say 100, and if the result is not we don't satisfy the result, we can increase to 200, for example, or 300, for example. Then we also, or you also can choose like the tolerancy, let's say maybe 0.1, maybe 0.2 or 0.1, for example. Yeah, but be careful for cluster with many overlapping like this. If you set the tolerancy is too small, maybe it's difficult. The time is very longer. Or if your cluster is not converged to one point, then it's very the program will run so long, because it's very difficult to get the tolerancy as low as this. Yeah, so for me myself, I prefer using maximum iteration in than tolerancy. Okay. Another difficult clustering is for k-means. Another difficult one is if the data density is different. So which one is our data density? Problem with k-means. Nah, this one. Okay. So after we visualize the data, and we see, oh, this is not. This one. The density of the data. They are very different to each other. One cluster is not quite dense, but two cluster they are so dense. So in this case, this is also a difficult problem for k-means. This one also a difficult case for k-means. Okay, so for difficult case for k-means, maybe we can set the initialization using better initialization, or the stopping criteria will be, we can increase the stopping criteria. Okay, clear? Any questions for k-means?
Yeah, for me it's clear. Yeah, came in.
Okay. Okay, so let me continue. Hmm. Oops. Oops. Okay. Okay, so if K means clear, then I will continue to hierarchical clustering. Okay, hierarchical clustering, it's a different approach with K-means. In K-means, K-means is partition-based clustering, and hierarchical clustering is hierarchical-based clustering. Eh, okay, so here, hierarchical clustering, it's produce a set of nested clusters, which is organized as hierarchical tree. So here you can see that there are so many nested cluster. So like maybe this is subcluster, subcluster. This is a bigger subcluster. A bigger subcluster is this cluster of like this belongs to the bigger cluster. A smaller subcluster is belongs to bigger cluster. Okay, or it can be represented like hierarchical tree. So for example, um, this hierarchical tree, we have data 1, 3. So this number, this is the index of the data. Okay, and this value is the distance. Okay, so for example, let's see data 1 and data 3. The distance between data 1 and data 3 is 0.05. So this one, 0.05. Okay. So hierarchical clustering, they will connect each data which has close to each other. So basically, it find two couple of data which has a smallest distance. For example, 1 and 3 is the smallest one. So 1 and 3 becomes to one subcluster. Okay. And which one? So here every time we will have a pairwise distance between each data point. So here we calculate again 1 and 3, 1 and 2, 1 and 5, and then 2 and 3, 2 and 4, 2 and 5. So all pairwise distance. And in our case, for example, 2 and 5 is the next smallest distance with around maybe around 0.08, for example. Yeah, so 2 and 5, the second and fifth data, it belongs to another one subcluster like this, another one subcluster. Okay, and if we already have like these two data or more than one data included into one subcluster, then they will have like average point between this, for example. Okay, so we find again the next subcluster, for example, like this. So maybe, oh, okay, we find the next distance, smallest distance is 2, 5, and 4. 2, 5, and 4. So that's why 2, 5, and 4 will be put in one subcluster like this. Okay, and then like this one, and continue again. So this is including into one, and the last one is all of the data. Okay, so basically this is the hierarchical clustering. Yeah, so this the hierarchical subcluster until all data belongs to one cluster. Okay, strength of hierarchical clustering. Compare with k-means. Hierarchical clustering, for the hierarchical clustering, we do not have to assume any particular number of cluster. Different like k-means. In k-means, we have to decide how many number of cluster at the beginning. But for hierarchical, because we will construct the cluster based on the distance, pairwise distance, so we don't need a number of cluster at the beginning. We just calculate the pairwise distance of each data point. Okay, and the hierarchical clustering also may correspond to a meaningful taxonomies. We usually can use hierarchical clustering, like if we want to do taxonomy, for example, for animal kingdom, or the type of what vegetable plant for plant, yeah, taxonomy, some meaningful taxonomy. Okay. There are two types of hierarchical clustering. The first one is agglomerative. The second one is divisive. Uh, the one that I just showed you before is agglomerative. It means that we start from each point as one individual cluster. So we have 1, 2, 3, 4, 5, for example. So we have 5 data points, each of them at the first step as the individual cluster. Then according to the pairwise distance, we see which two data is close to each other. For example, these two. Okay. Then continue. Which one is smaller again? Maybe like this, for example. So this is the second one, and then the third one, and then the fourth one. Yeah. So we start from individual point as the individual cluster until all data in one cluster. Okay. Divisive is the uh, inverse of the agglomerative. So we start from one cluster. So in divisive, all data points, it belongs to one cluster, like this. The first one, all data points belong to one cluster, and then we split each step. We split the cluster. So maybe we split like this. The first one, this is cluster 1, cluster 2, and then another splitting maybe like this, 1, 2, 3. We split again, maybe like this, and split again. We split all the clusters until each cluster only contains one point, like this, 1, 1, 1, 1, 1. Okay. So agglomerative is from one data point to all data point in one cluster. Divisive is from all data point in one cluster into one data point in one cluster. Okay. Traditional hierarchical clustering usually use similarity or distance matrix to merge or split one cluster at one time. Yeah, the easiest one is using similarity or distance matrix. Okay, this is we start from agglomerative clustering algorithm. Yeah, the idea is successively merge closest cluster. Okay, so we will have a proximity matrix to calculate distance from each data point to other data points, and then let each data point be a cluster. So because we start from one data in one cluster. Okay, and then we repeat this step, merge two closest cluster, and then we update the proximity matrix until only a single cluster remaining. Okay, okay. This is the example. Sorry, give me 2 minutes. I want to take some water. Okay, so here, eh, okay. Um, for example, this is the data P1, P2, 3, 4 until 12 data. We have the proximity matrix, distance matrix. Sorry, the proximity is the general terms. In traditional way, proximity refers to distance or similarity. For example, we use distance using Euclidean distance. So here, in this matrix, we will fill this with the Euclidean distance, for example, between P1 and P2. So distance between P1 and P2, for example. This is distance between P1 and P3, and then for all of this. Yeah. Okay. Start with cluster of individual point and a proximity matrix. So we start from this, and then we will merge two data points which has the smallest distance, because we use distance here. Okay, so let's say, for example, oh, this is the close to each other, belongs to 1, and this one is also close, and then this one is also close, for example, and this one is also close, for example. Okay, and then after we put the smallest distance, we can update the condition. You can see here at the first time we have proximity matrix for each data point. It means that we calculate distance between each data point. But after one merging step, okay, for example, P1 it belong to P2, P1 and P2 in 1, P2 and 3, P3 in 1, and for the rest also the same. For example, like this. Yeah. Now we have a small cluster C1, C2, 3, 4, and 5. So the proximity matrix now is between the clusters, like this. Okay, so if we have a cluster now, how to how to calculate the proximity matrix? In what distance we have to put here? For example, in C1, there are 2 data points. C2, there are 2 data points. 3, I think there are 3 data points here. 4 also have 3 data points. 5, they have 2 data points. Yeah. We can, for example, we can use many measurements to represent the proximity matrix. Okay, maybe the easiest one, because we learned about k-means already. One example to calculate the proximity matrix, if we have the small cluster already, we can calculate the centroid. For example, for C1 we have data 1 and data 2, then we calculate the average. Oh, maybe this one is the centroid. And C2, for example, this is the centroid, so we calculate the distance between centroid 1 and centroid 2. So this will be the result of this proximity matrix. So this is M1, M2, distance between centroid 1 and centroid 2. Remember, centroid is only one of several ways to represent the proximity matrix. Okay, then after that after we treat this as one point, okay, we can have a more or further assignment or further merge. For example, oh, C2 and C5 is close to each other, so we can merge this like this. Yeah, until all of this. Okay, so here, how to represent the proximity matrix if we have like this between different subcluster. Okay, we can use what we call it min, max, group average, distance between centroid, the one that I just saw before, and other algorithms defined by objective function. Yeah, so now our proximity matrix is we have to calculate similarity between two subcluster. Okay, for example, if we use min, okay, min proximity matrix using min defined by the minimum or the closest data point between two cluster. For example, we have cluster 1, cluster 2. Okay, so in cluster 1 we have data 1, data 2, data 3, data 4. In cluster 2 we have data 5, data 6, 7, and 8, for example. And then mean is the minimum point between this data point. Between two cluster. So we have to calculate distance between each other. For example, we calculate distance between D1 and D5, D1 and D6, data 1, data 1 and data 7, data 1 and data 8, for example. Maybe not like this. I have to data 1, data 2, data 3, data 4. We calculate distance with data 5, data 6, data 7, and data 8. So we calculate the distance. Data 1, 1 to 5, 1 to 6, 1 to 7 and 8, and then 2 to 5, 2 to 6, 2 to 7, 2 to 8, until 4 to 8. And from all of this value, which one is the minimum one? Okay, finally we get the minimum one is D3 to D5, or the closest one is D3 and D5. Okay, so minimum value for cluster 1 and cluster 2 is like this. Distance between D3 and D5. Okay, is it clear?
Very clear for me. I don't know for other.
It's clear? For example, this is in Philippines have so many islands, yeah, and in Indonesia also have so many islands. So distance between Philippines and Indonesia is the closest islands of Philippines, maybe here, and maybe Indonesia is, oh, wah, disappear. This is the Philippines. You have so many islands here, and Indonesia is above Philippines. So here, bigger island, and we have so many islands here. So the distance between Philippines and Indonesia is defined by like this, the small one, this one, the closest distance. Okay, this is for min. Oh, this one, this is for min. This is Indonesia. So using the smallest distance. Okay, but for max, okay, for maximum, a little bit similar with the minimum, but here we use the farthest point. So distance between Philippines and Indonesia defined by the farthest point. So here with here. So this is the distance. Okay, so for example, this is cluster 1, cluster 2. Okay, if we use max, then we calculate the maximum distance between data in cluster 1 and data in cluster 2. Okay, the third one, we can use group average. In this case, we calculate all pairwise distance. So we have like this 2, 3, 4, 5, 6, 7, 8. So we have the distance between 1, 2, 3, 4 with 5, 6, 7, 8. We have the distance of each other of this, and then we take average of all distance. Yeah, so this is group average. Okay, how about centroid is the one I just mentioned before. It's just like a k-mean. So if we want to calculate distance between two clusters, so each cluster represented by centroid, and we calculate distance between these two centroids. Okay. Yeah, so this is what we can use for what we can use to define the proximity matrix. So we can use the proximity matrix to develop the dendrogram. Dendrogram is the one like this. Yeah, this is the dendrogram. Okay, minimum or single link. Proximity of two clusters is based on the two closest point in the different cluster. Yeah, this is using mean, for example. This is the okay. Now if we have, for example, this is our data 1, 2, 3, 4, 5. This is the distance matrix. Okay, so if we define the proximity matrix as the minimum, okay, then this is the step-by-step of the agglomerative algorithm. First is we find the smallest one. Which one is the smallest one? So the smallest one may be, is it this one? 0.11. 0.11 belongs to data 3 and data 6. So data 3 and data 6 will be located in one subcluster. Okay. And then 2 and 5 is the one subcluster. And then this one, and then this one, and then this one. Okay. Sorry. At these steps, yeah, after we put data 3 and 6 in one subcluster, then of course our proximity matrix here is also updated. So our proximity matrix will be P1, P2, and this one P3 and P6, 1, 2, 3, 4, and 5. This one also P1, P2, P3, and P6, P4, and P5. Okay. So if you ask me, oh, so P1 distance P1 to P2 is still using within distance because this is still 1 point, this is still 1 point. But how about P1 to P3 and 6? So here, after we get this, if we use mean and we want to calculate distance between this data point 1 and 2 here, then we have to calculate distance between 1 to 3 and also 1 to 6. For example, 1 to 3 is 0.3, for example. 1 to 6 is 0.5. So distance P1 and P3, P6 is the minimum one, 0.3. Also for P4, for example. So P4 to here. So we have to calculate distance between 4 and 3 and 4 and 6. So that if we use the smallest one, for example, this is 0.2, this is 0.6, then the distance between P4 and P3 and P6 is 0.2. Okay. Then after we update the proximity matrix here, we search again which one is the smallest one. Oh, the smallest one is 5 and 2, for example. Okay, and continue again, update the proximity matrix. In this case, after we have 3, 6, and 5, 2 in one subcluster, so our proximity matrix is only P1, P2, and P5, P3 and P6, P4. This one, P1, P2 and P5, P3 and 6, P4. Okay, then we calculate again. Okay, until all in one cluster. Okay, now
Dr. Ferrer, excuse me.
yes, yes, yes.
How do we calculate the proximity between P2, P5, and P3,
I also want to
P6?
ask that. I also want to ask that.
P2, what?
Exactly.
P2,
P2, P5 to P3
Yeah.
and P6.
okay, P2, P5, and
Mm,
P2 and P3.
Yeah. I
P2
also want
and
to ask that
5
one.
and P3 and P, right? Yeah. Okay. So, wait, I prepare one empty because it's full.
The red number one and number two. Yeah, that one. I got confused.
Yeah.
Yeah, that one.
Okay.
Yeah.
Okay, like this. So we calculate distance, for example, 2 and 3. Let's say, for example, 2 and 3 is 0.2, for example. And then 2 and 6, for example, this is 0.6. And then 5 to 3, for example, this is 0.7, and 5 to 5 to 6, 0.8, for example. So because we define proximity metric as minimum value, so we find out which one is the smallest one, 0.3, right here. So distance between P2, P5 and P3, P6 is 0.3. Is it clear?
Okay. Thank you.
Yeah, this one, if we don't forget this one, if we define proximity matrix using mean value. Okay. Yeah.
Oh, okay. I got it. Okay. Clear for me.
Mhm.
Yeah. Mhm.
Okay, Arvin, is it clear?
Yes, Dr. Ferrer, thank you.
Okay, yeah. Okay, and now this is the strength of mean if we define the proximity matrix using minimum value. So this one, we can handle non-elliptical shapes, which is the drawbacks of the k-means. If we apply k-mean, if our data is like this, you see the shape is so irregular, we use k-means, the result may be not as good as this, because k-means usually the shape of the cluster for k-means is elliptical or round one, maybe like this, 1, 2, 3, 4 for k-means. Yeah, but we use hierarchical using mean, it can solve this kind of cluster. Okay. However, of course, it also has limitations. So one limitation of the mean hierarchical proximity is using minimum. It is also sensitive to noise. For example, we have this original data points, and you can see, like, for example, here almost like it can belongs to here, the left one it can belongs to the right one. So in this case, maybe if we divided data point into two cluster, so maybe this one belongs to one cluster and this one belongs to one cluster. It can happen. Okay. Or if we use three clusters, so this is very weird. So this one is one cluster, this one is one cluster, and small one is another one cluster. Yeah, so be careful with noise. If you compare with this data point, this data set, the shape is irregular, but there's no noise. So uh, like this, no, for example, like close to each, very close to each other. There is no such a noise here. So it's okay for this algorithm. But if we have noise, then maybe the result will not be clear or will not be good. Okay. Then if we use maximum, now we use maximum or complete linkage as the proximity. So maximum or complete linkage is this one. Uh, this one. This is the complete linkage. All of this data is we consider all distance between all pairways of the data or maximum like this. Yeah. What happens if we use these two as the proximity matrix? Okay. So if we use maximum, for example, this is belongs to one, this is belong to another one. Okay. This belongs to the next one, and next one, the last one. Okay, so different proximity matrix will give us different dendrogram or different steps in clustering. Okay, strength of maximum. If we use maximize as the proximity matrix, it will be less influenced by the noise. So if our problems maybe has some noise like this, it is better to use maximize as the proximity matrix than using minimize. So these problems, if we use minimize before, the result is not quite good, but if we use maximum, the result is better. A limitation. Okay, a limitation if we use maximums. Usually or sometimes it tends to break large cluster. For example, like this, the cluster is very big compared to another cluster. Okay, so in that case, maybe the result will be like this. Yeah, so the bigger cluster is divided into two cluster. Okay, it's also sensitive with the globular cluster. Yeah, bias toward globular cluster. A little bit similar with the K-means. Okay. Group average. Okay, so group average, the one if we use average of pairwise proximity using the one if we have many data point here, so we calculate all distance and we average the distance. Okay, so what happens if we use group average? Okay, this is the dendrogram like this. Okay, group average compromise between single and complete link. Okay, the strength is less susceptible to noise. So if the data has a little bit similar with if we use maximum, so it's if our data has some noise, it's better to use maximum or group average. But again, the limitation is biased towards globular clusters. So yeah, so we can choose the proximity matrix based on our visualization, data visualizations. Okay. Another example is using Warts methods. Okay, so for Warts methods, it is also complete, similar like complete linkage. So similarity of the cluster is based on the increase in square error when two clusters are merged. Okay, so it's merge the cluster first and then calculate the increase of SSE. For example, we have this one C1, we have this one C2. Okay, C1 has SSE, C2 has SSE, and then the Warts methods. If we use Warts method as the proximity, then we calculate the total SSE if we merge this and we have SSE. And then the differences between SSE with small one and after we merge, this is the distance of or proximity. Okay, the positive or the advantages is less susceptible to noise, but again, this one is disadvantage is biased towards globular cluster. Okay, okay, so we actually, if we back to k-means, and if we want to solve like a number of the initialization, random initialization, we can apply actually hierarchical clustering to get a better initial point, random point, initial centroid for the k-means. Now we can apply this to handle the k-means. Okay, so this is the comparisons. There are 4 different proximity. Okay, what's maximum, minimum. Okay, and then next step here, the second step still the same here, the third step. Okay, see here, for minimum, if we use minimum for the proximity at the third step, this belongs to 5, 2, 3, 6 belongs to one cluster. But for maximum Warts and group average, at the third step, 3, 6, and 4 becomes to one cluster. Okay, and fourth step is different. Yeah, each of them are different for the fourth step. Finally, the fifth step. Oh, sorry. Yeah, so this is the differences comparison if we want to compare hierarchical clustering using different proximity metrics. Okay. Okay, this is the the complexity of the hierarchical clustering. Yeah, so this is the space used for the proximity metrics and the time in many cases. So this is the big complexity of the hierarchical clustering. Okay, any question until this? No questions? Is it clear?
So far it's clear.
So far, it's
Okay.
clear, Dr. Farah.
Okay, so let me try to find scalar for hierarchical clustering. Okay, so oops. Okay, this one is package from Python for clustering. It provides already k-means, the one that I just showed you before, and for hierarchical, it is this one, hierarchical clustering. Okay, so here in hierarchical clustering, for the linkage of or the proximity matrix, they provide like wards, and then maximum or complete linkage, and then average linkage, and single linkage. So if in the Python they give information about this, hopefully you know already which one you want to use. Okay, and yeah, here different result if we use different proximity matrix. So like this, for example, try to make it bigger. Okay, so for example, the first data set, this one, if we use single linkage, minimum one, like this, the result, these three, this average, complete, and ward linkage result relatively similar. So for this type of problems, it is better to use single linkage. Okay, the second data point, again, like this. Yeah, so single linkage is better than other three. Okay, this is the third data point. I think for the third data points, single linkage is not better than other three. So maybe the best one is word linkage, like this. And for the fourth data set, I guess all of them is perform not quite well. Maybe the better one is again this one, word linkage. This one for the next data set, all of them can give a better results. Because this is very easy, you can see that the fifth one, all data points, they have the same size, the same density, and well separated, no overlapping, no noise. So all of them can give us as best result as or the best result. Okay, next data point. Okay, like this. Yeah, so in general, my suggestion, if our data set, we do visualization first. Then from the visualization, we see that, oh, if this size, no, this shape of the cluster is uh, irregular like this, for like the 1 and 2 data point, it is better to use single linkage. But if the data point have many noises like this, it is better to use single linkage.
No questions for me, Doc Vera.
Okay, good. Then you can try. You can start to try. Yeah, and here in the internet, in the package, they give you example already. For example, k-means here, and then if you open this, then they give you the example of k-means. Where is it? This one. K-means you can try here. You just simply copy this program, and then you can run your programs, and you can try. And if you want to try hierarchical clustering, they also have give us this one. This is the agglomerative clustering, hierarchical, and then this one is the example. you can try. Okay. No more questions? Okay. If no more questions, then I think I can finish our class today. So see you next 2 weeks.